Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about motional EMF. Okay, so let's set the stage by considering what would happen if I had a long piece of conducting material like this. So this is a conductor. And therefore charges can move about freely in this material. Okay, now let's assume that I'm allowing this conductor to move. It could be falling, it could just be moving in general. Let's say maybe it's sliding with some constant velocity v. Let's also assume that locally I have a magnetic field. All right. So magnetic field basically means that I'm going to have a force on any charges that are in the material. Maybe my magnetic field is oriented this way. It's going to be a uniform field. So let's draw that. So this bar is moving in this magnetic field. And now let's consider a charged particle. Maybe the charged particle is, say, an electron hole. So it's a positively charged particle. So using our right-hand rule, we have QV. V is kind of down along the page. B is up out of the page. So B is out of the page, V is down the page. That actually means that we're going to get a force on this charge in this direction. And similarly, if I have a negatively charged particle, say an electron, then I should expect a force in this direction to act on that electron. Okay, so essentially what I would expect to have happen is as this piece of metal moves through the field and this force is acting on these particles, I expect there to start to be some sort of a buildup of charges so that I end up with a bunch of positive charges on one end of the metal and a bunch of negative charges on the other end of the metal, like this. But since I have a bunch of plus charges here and minus charges here, I also expect there to start to be an electric field. So if I draw the electric field, more or less, this isn't a very good drawing, but more or less, the electric field lines I expect to point from the plus charges side to the minus charges side, like so. Okay, now let's consider again another charged particle. So right here is another charged particle. We'll make it a positive charge. We could use a positive or a negative. I continue to have a force in this direction from the magnetic field. This force that I originally drew was from the magnetic field. But I now also have in the opposite direction on that same force, let's draw it in a different color though. In the opposite direction on that same particle, I have a force that is due to the electric field. We'll call that F sub E. It's a positive particle, positive charge, so the force is in the direction of the field. Now at some point, FE and FB will have equal magnitude while acting in opposite directions. So FB is equal to FE when, and brief calculation, we know that FE is Q times E, and we know that FB in this case is QVB, and then depending on the actual orientation of the field and the velocity vector, there could be a sine theta term, so we'll just throw a sine theta in there as well. So when this and this are equal, so QE is equal to QVB sine theta. Or in other words, when V is equal to E divided by B sine theta. There's Q's on both sides, so if I divide out a Q from both sides, then the Q's will cancel, and I'm dividing out a B sine theta from both sides. Okay, and that gets me this equation right here. So when this is true, then this right here is true, or this right here reaches a true point. I have to get some charge separation first, but that's fairly quick. And at this point, you have equilibrium. So this is equilibrium for the electrostatic and for the magnetic force. So equilibrium means that this particle will no longer be displaced one way or the other anymore. Well, if we look again at just this metal conductor, and again, I put onto this metal conductor some charge separation. So maybe I have on one side, I have a bunch of negative charge or of positive charges, and on the other side, I have a bunch of negative charges. Really should be about an equal number. This is starting to look more or less like the case that you get for plates on a capacitor, in that you have a bunch of plus charges here and a bunch of minus charges here. So this looks kind of like a positively charged plate separated in space from a negatively charged plate. And you know that the E field that goes with that, again, is just going to point from plus side to minus side for the capacitor. And you know that here it just points from plus side to minus side for this device, essentially. For the capacitor, we know that the difference in voltage between the two plates, the voltage drop, is equal to E times D. So if this distance right here is D and this right here is the E field, then delta V should be E times D. That's just for a uniform field. It follows that if this piece of metal has a length L from one end to the other, that there's going to be a voltage drop. Delta V is E times L. But going back to this previous slide, V is E over B sine theta. We also could have written this as E is equal to V times B times sine of theta. So these two equations are equivalent to each other. So that means that my delta V, my voltage drop between these two ends, delta V, will look like V times B times L times sine of theta. Now, because this is not just a voltage drop, but actually is a, in some sense, like pump for moving the charges, it follows that this delta V is actually equivalent to the EMF produced by moving this through our magnetic field. In other words, if I were to run a pair of tracks beneath this, then these charges wouldn't just build up on the ends. They would actually be able to flow, assuming that you have a good contact, they'd be able to flow through the conducting tracks. And so you have really an electromotive force here. Really, it's acting kind of like a battery in that sense. And so we could say that motional EMF, E MF mote is V times B times L times sine of theta. Now, to see what I mean by a pair of tracks underneath it, let's come back to the same situation, and this time I'm going to draw it so that I've got my moving piece of metal, and then maybe beneath this piece of metal there are a couple of let's say conducting tracks, and maybe the conducting tracks are just kind of like this on one side. Then over here you got another pair of conducting tracks down here. And maybe you've got, let's say, a wire or a resistor or something like that connecting the other end. So it's a closed circuit now. Well, that means that these negative charges that are being pushed over here can actually continue through in this direction, and the positive charges, the electron holes that are being pushed through, instead of ending right here, can continue to circulate this way. So that means that I now have a current within this system. So I have a current due to motional EMF. Okay, well, how much current? Well, essentially we would expect I motional to be equal to the motional EMF divided by the resistance of your system. Given that this is an algebra-based system, an algebra-based class, we'll assume that there's some element in here that has a large enough resistance that the changing resistance from the tracks getting effectively like shorter in the circuit is negligible. Okay, but I do have a complete circuit. This thing right here is sort of like now my battery source for this circuit. And the EMF for the battery is the motional EMF is V times B times L times sine theta. Okay, so now I've got current flowing. Let's conclude this with an example. All right, so our example is a bit wordy. You just have a bar, its length is 1.2 meters, it's sliding at constant speed along a pair of tracks, assuming that everything is conducting here, which are 1 meter apart, and of course like connected on the far end. And all of this is happening in a uniform magnetic field of magnitude 0.75 teslas. The bar's velocity is at 6 meters per second within the horizontal plane. You could take it as being in the y direction specifically. And the magnetic field is along the velocity vector but elevated by 60 degrees. That essentially means that the magnetic field looks like this relative to velocity. So you've got your velocity vector here, you've got your magnetic field 60 degrees with respect to it. And you'll notice that I've said length is 1.2 meter, but the bars are 1 meter apart. That means that 1 meter is effectively the L. So if I come back up here to this diagram, L is actually the distance between your two tracks in this case, not the length of the bar, since that is the distance along which these charges will move. So coming back to the problem we can solve, the EMF is equal to the magnetic field strength times the distance between the tracks times the speed times the sine of that angle theta. So we actually can just plug the numbers in from this problem. So L, B, theta, and V. And what we get is that the EMF is about 3.897. So let's call that 3.9 volts. And that's it. That's our problem.